Concrete provides the compressive strength that makes modern skyscrapers and bridges possible. It handles massive, crushing weight without flinching. But it has a fatal flaw. While it can take being crushed, concrete has virtually zero tensile strength. If you try to bend it or pull it apart, it snaps. Hardware is the only thing preventing tension failure, but navigating a catalog of fasteners, fibers, and epoxies can be paralyzing. There are thousands of options to sort through. Choosing the wrong hardware creates a catastrophic structural liability. This is true whether you are hanging a simple ledger board for a deck or securing a heavy commercial door frame. To identify the right hardware, we have to look at why connections fail. On the job site, hardware typically fails in one of three ways. This failure scorecard helps categorize the risks. First is load mismatch. This happens when you confuse shear force, the weight pushing perpendicular against a bolt, with pull-out force, which is tension pulling the bolt straight out of the hole. Second is environmental corrosion. Because concrete is porous, moisture inevitably creeps in. When that water hits internal steel, the metal rusts and expands, cracking the slab from the inside out. Third is improper installation. The most common culprit is leaving dust inside a drilled hole, which physically blocks chemical adhesives from bonding to the concrete. Surviving these threats means matching the exact mechanics or chemistry of the hardware to the specific scenario. This diagram maps out our hardware choices, branching into two paths. We'll start with internal reinforcement, the materials you place before the concrete is poured. Traditional steel rebar and wire mesh are the baseline standards. They have been the go-to choice for decades. Steel provides universally accepted, code-compliant tensile strength. Engineers can calculate its performance with high precision. However, steel requires significant manual labor to tie the mesh together. It is also vulnerable to rust if moisture ever penetrates the concrete. The modern alternative for flatwork and tunneling is polymer-based macrosynthetic fibers. Mixing these fibers into wet concrete eliminates the time needed to lay steel mesh. Because they are synthetic, they are also immune to rust and corrosion. But fibers have limits. They require precise mix design batching and cannot replace heavy structural rebar in deep tension scenarios without an engineer's approval. Replacing steel with synthetic fiber is an ROI calculation. You trade higher upfront material costs for labor savings and zero long-term corrosion liability. The second branch is external anchoring. These are the fasteners used to attach materials to concrete that has already cured. For light to medium-duty work, we use mechanical fasteners, like threaded concrete screws and expanding sleeve anchors. These allow for fast installation with immediate load-bearing capacity for static, non-moving weights. The trade-off is their limited strength. They possess lower shear and pull-out limits compared to heavy-duty options, meaning they cannot handle high vibration. For indoor, non-structural attachments like conduit or handrails, these mechanical fasteners are the most efficient option. In heavy-duty external anchoring, the structural stakes are at their highest. Here, the choice splits into two options: wedge anchors and chemical adhesives. The wedge anchor is the industry standard for high-load mechanical fastening. Torquing a wedge anchor delivers massive pull-out and shear strength. It is ideal for securing structural steel and machinery. However, wedge anchors hold their weight by expanding inside the hole. This puts extreme outward pressure on the surrounding concrete. Because of this pressure, wedge anchors can crack and shatter the concrete if they are placed too close to an edge. Chemical and adhesive anchors provide a solution for edge placement and high vibration. Injecting a two-part epoxy creates a load-bearing bond that can exceed 5,000 pounds. It puts zero expansion stress on the concrete. Because they rely on chemical bonding rather than physical friction, adhesives are the safe choice for vibrating loads or seismic retrofits. The trade-off is that chemical anchors are unforgiving to install. If you do not meticulously brush and blow every trace of dust out of the hole, the bond will fail. Choosing between heavy wedge anchors and chemical adhesives is a trade-off between foolproof installation and high-performance edge-safe capability. This decision matrix maps your load type against the environment. DIYers or builders working indoors land in the light static, dry quadrant. Optimize for speed using concrete screws and sleeve anchors. Heavy contractors lifting stationary loads indoors hit the heavy static dry quadrant. In this quadrant, use wedge anchors, provided they are far from edges, and traditional steel rebar where moisture is blocked. For bridge work, structural retrofits, or exposed slab pours, you land in the heavy dynamic wet quadrant. When loads are dynamic and environments are wet, mechanics alone often fail. The acceptable choices are advanced chemical bonding and synthetic reinforcement. If you are using advanced adhesives, following the whole cleaning protocol exactly is mandatory. If dust remains, the bond will fail. Estimators should note that while synthetic fibers cost more upfront, they remove steel laying labor and corrosion risks from the total cost of the project. For light builders, do not over-engineer. If the load is static and dry, standard mechanical anchors are sufficient.
Every bolt and epoxy tube serves as a structural insurance policy against the laws of physics. Buy the exact policy required